Welcome. In this session, we'll explore some of the linear algebra of a layer of artificial neurons. So the idea behind a layer of artificial neurons is that they all receive the same inputs and then they're producing different outputs. So let's imagine that what we're given is we're given a design matrix X, and then we're given regression values or dependent values as a matrix Y, and let's say that it's one set of regression values and a second set of regression values. So these aren't necessarily labels, these are real numbers, and what we want to do is we want to take these data and we want to do two regressions simultaneously. Well, of course we could just separate them into two problems, but using the material in the previous sessions, we can gather those into a single problem. So what we'll have here is we'll use two weight vectors. And so we'll refer to those weight vectors as weight vector 1 and weight vector 2. So our predictions then are, our first prediction will be the design matrix times the first weight vector, and our second prediction will be the design matrix times the second weight vector. And what we could do is we could gather the predictions as, and we could say that that's a matrix U, which will be here the U vector 1 and the U vector 2. And then we'll gather the weights also as a matrix W that we will define here as weight vector 1 and weight vector 2. And so our predictions are that the predictions are the design matrix times the weight matrix. And the regression that we're supposing we want to perform is we want this X design matrix times the weight matrix to be approximately the given regression matrix. So the question is, how can we solve for W? And yes, we could divide this into two problems and solve for W1, W2, and then gather them together. If we use the material from the previous sessions, we can solve this a different way. So let's consider the Kronecker product and the vectorization function. So we could write this problem of the design matrix times the unknown weight vector being approximately the regression, and we could rewrite using the Kronecker vectorization theorem. We would write this as the identity Kronecker product with the design matrix times the vectorization of the weight matrix is approximately the vectorization of the regression values. And that's equivalent to saying that the Kronecker product of the identity and the design matrix times a big weight vector W is approximately equal to a big weight vector Y. And here we have to be sure that we're distinguishing this W is no longer W1, W2 individually. It's W1 appended with W2. That is, it's the vectorization of this matrix. And y is not just an individual regression value, y is the vectorization of that matrix. So we can then solve for the vector w as some estimated value, and then we can reshape into an optimal w star, which is the reshape of the computed weight vector, and this would then have m rows, because that's how many observations are in our design matrix and in our regression values, and it would have 2 columns because we're considering only 2. This number, of course, might change, and it might be some value L, which is larger than 2. So this is an example for 2 neurons of how we could, given some original data and given multiple regression values on that data, we can solve this as a single problem using linear algebra.